Hello everyone. Welcome to the video lecture series on Chemical Engineering Thermodynamics 2. Myself, Jamin Pandya, Assistant Professor in Chemical Engineering Department of LJIET Institute of Engineering and Technology. So let's continue with the chapter Phase Equilibria. In this lecture, we'll talk about the vapor-liquid equilibrium, the nature of equilibrium, the phase rule and Duhame's theorem. So let's start with introduction of vapor-liquid equilibrium. A system is said to be in equilibrium if no change occurs within a system when it is isolated from surrounding. An isolated system is in mechanical equilibrium if no change occurs in pressure, where in thermal equilibrium if no change occurs in temperature. In phase equilibrium, if no transition formation from the one phase to another, then can say that the system is phase equilibrium. In chemical equilibrium, if no change occurs in chemical composition of system, then that type of equilibrium is known as a chemical equilibrium. The condition of mechanical equilibrium and thermal equilibrium are straightforward, but the condition of a chemical and phase equilibrium can be complex. The equilibrium criteria for reacting system is based on second law of thermodynamics. More specifically, the increase of entropy principle. For adiabatic system, chemical equilibrium is established when entropy of the reacting system reach maximum. Most of reacting system encountered in practice are not adiabatically. However, therefore we need to develop equilibrium criteria applicable to any reacting system. We develop the general criteria for chemical equilibrium and apply it to reaction ideal gas mixture or ideal liquid mixture. So let's talk about the phase equilibria and criteria for the chemical equilibrium and nature of chemical equilibrium. To understand criteria for chemical equilibrium, consider a reaction chamber that contains a mixture of CO, O2 and CO2 at specific temperature and pressure. Let us try to predict what will happen in this chamber. Probably the first thing that comes into mind is chemical reaction between CO plus O2 to form CO2. This reaction is certainly possible, but it is not only possibility. It is also possible that CO2 in this combustion chamber deassociated in CO plus O2. Yet, third possibility will be have no reaction among the three components at all. Therefore, the system is to be in chemical equilibrium. It appears that although we know the temperature, pressure and composition of the system, we are unable to predict whether the system is in chemical equilibrium or not. Assume that CO2 and CO2 mixture are maintained above in chemical equilibrium at specific temperature and pressure. The chemical composition of this mixture does not change unless the temperature or pressure of mixture change. That is, reacting mixture in general has different equilibrium composition at different pressure and temperature. Therefore, when developing a general criteria for chemical equilibrium, we consider reacting system at fixed temperature and pressure. Taking to positive direction of heat transfer to a system, increase a entropy of principle for reacting and non-reacting system was expressed by the equation that can be given by ds less than equal to del q upon t. A system and surrounding from the adiabatic system, and for such a system reduced to ds less than equal to 0. That is, chemical reaction adiabatically chamber proceed in a direction of increase in entropy. When the entropy reach a maximum, reaction stop. Therefore, entropy is very useful property in analysis of reacting adiabatic system. When the reaction system involve heat transfer, the increase of entropy principal relation that can be given by this equation, which becomes impractical to use. However, since it requires acknowledgement of heat transfer between system and surrounding, a more practical approach would be develop relation for equilibrium criteria in terms of property of the reacting system only. To understand this, let's consider a reacting or non-reacting simple compressible system of fixed mass with quasi-equilibrium work model at specific temperature T and pressure P as shown in this figure. Combining the first and second law relation for system that can be given by del q minus pdv is equal to du and del s less than equal to dq upon t, which gives du plus pdv minus t ds less than equal to 0. The differential of Gibbs function that can be given by g is equal to h minus ts. At constant temperature and pressure, it becomes dg is equal to dh minus tds minus sdt. Now, if we are going to replace this value of dh, we will get du plus pdv plus vdp minus tds minus sdt. So, this plus vdp and minus sdt will be cancelled due to the constant pressure and constant temperature. So, this equation becomes dg is equal to du plus pdv minus tds. Therefore, chemical relation at specific temperature and pressure proceed in direction of decreasing Gibbs function. The reaction stops and chemical equilibrium is established when the Gibbs function attains minimum value. Therefore, criteria for chemical equilibrium can be expressed as a dg at constant temperature and pressure is equal to 0. The chemical reaction at specified temperature and pressure cannot proceed in direction of increased Gibbs function, since this will be a violation of second law of thermodynamics. Notice that if the temperature or the pressure is changed, reaction system will assume a different equilibrium state, which is a state of minimum Gibbs function at new temperature and pressure. To obtain relation for the chemical equilibrium in term of property, the individual composition considers a mixture of 4 chemical components. Let's suppose A, B, C and D that exist in equilibrium at specified temperature and pressure. Let the number of mole of respective component Na, Nb, Nc and Nd. Now consider a reaction that occur to infinitesimal extent during which different amount of A and B are converted into the C and D, which is a product, where A and B which is a reactant and C and D which is a product, while the temperature and pressure remain constant. The equilibrium criteria requires that the change in Gibbs function of mixture during the process to be a 0. So, where the Gibbs free energy or Gibbs function at specific temperature and pressure and number of moles are different change in number of mole of that particular component. Notice that if the temperature or the pressure is changed, the reacting system will assume a different equilibrium state, which is a state of minimum Gibbs function at new temperature or pressure. So this is all about the criteria of the equilibrium and nature of equilibrium. So let's talk about phase rule for non-reacting system. The essence of phase equilibrium problem is to express quantitatively the relationship between the variable that describe the state of equilibrium of two or more homogeneous phase, which are free to interchange energy and matter. For homogeneous phase at equilibrium, the intensive property are same everywhere. In phase equilibrium study, the intensive property of interest are pressure, temperature, density and composition. The phase rule allow to determine the number of degree of freedom denoted by the F, which are the number of independent variable that must be arbitrary fixed so that establish uniquely the intensive state of system. The phase rule was developed by J. Willard Gibbs in 1875. The commonly used as a phase rule variable are temperature, pressure and composition. By specifying this, the intensive state of system at equilibrium is uniquely established. However, all these variables may not be independent. The phase rule gives the number of variables from set which when arbitrarily specified would be establish the remaining variable as a fixed value, thus by the degree of freedom. We mean number of intensive property that can change without changing the number of phase or number of component in any phase. Let's consider homogeneous phase of pure substance like water contained in beaker or carbon dioxide gas confined in cylinder. The state of system is determined whenever two properties are set at definite value. Here the number of degree of freedom is 2. The number is not necessary 2 for more complex system. For example, mixture of system and liquid water in equilibrium at 101.3 kilopascal can exist only at 373.15 Kelvin. It is impossible to change the temperature without changing the pressure. If the liquid and vapor to continue to exist in equilibrium, the number of degree of freedom in this case is only 1. For we can exercise independent control over the only one variable, either the temperature or pressure, and not both. It is evident that there is a connection between the number of degree of freedom, number of phase in equilibrium, and number of component and constituent system. The phase rule relationship that can be given by F is equal to C minus P plus 2, or can say that F is equal to N minus P plus 2. The phase rule can be derived using the equilibrium criteria, considering a heterogeneous system consisting of C component distributed between P phase or N component. The composition of phase containing N component is determined by the specifying C minus 1 concentration term. This is become if mole fraction of all but one of component in mixture are known. The mole fraction of the remaining component is a difference between 1 and sum of the component C minus 1, or can say that N minus 1. Since there are phase, the number of concentration variable required to define the state of system that can be given by P into C minus 1. Recognizing that the temperature and pressure are also to be specified, so can say that total number of variable that can be given by P into C minus 1 plus 2. The fact that system in thermodynamic equilibrium implies that system obey principle of equality of chemical potential. Therefore, all concentration are not independent. The concentration of component in different phase are interrelated such that chemical potential is the same in all phase. For any component, there are exist P minus 1 equation connecting the concentration in P phase. Since there are component C, there are P minus 1 into C independent equation which automatically fix. So number of variables that are not independent that can be given by C into P minus 1. The number of degree of freedom, which is equal to number of variable that independent and hence must be arbitrary fixed to define the system completely, is obtained by difference between the number of variable minus number of equation. So that equation becomes F is equal to P into C minus 1 plus 2 minus C into P minus 1. We can replace this C with N, both are same. Equation, by rearranging this equation we will get F is equal to C minus P plus 2. This equation is known as a phase rule derived by the Gibbs. It may be noted that if particular component is absent for any phase, number of composition variable is reduced correspondingly. At the same time, there will be a similar decrease in number of independent equation. The result in equation is valid even if all components are not present in every phase. The number C, which stands for the number of components to be used in equation, is a least number of independent chemical compound from which the system can be created. This becomes important in dealing with the system involving chemical reaction. To understand this, let's take one example. For example, If system considering of methanol, hydrogen and carbon monoxide is at equilibrium, the number of components is only one. A chemical reaction CO plus 2H2 gives CH3OH occurs in system. The phase rule for reacting system will be discussed in chapter number 3. As an example of application of phase rule, consider homogeneous system of single substance. Here C is equal to 1, P is equal to 1, therefore F becomes 2. Two variables says temperature and pressure are to be specified to define the state of system. Consider two-phase system. For the example, pure liquid water in equilibrium with its vapor. So here C is equal to 1, P is equal to 2. So F becomes 1. One intensive property, either pressure or temperature, but not both may be changed freely. If solid is also present in the system, then P becomes 3 and F becomes 0. So in this case, no intensive property can be changed and specification that three phases are in equilibrium, fixed temperature and pressure. The triple point of water is at 273.16 Kelvin and 618 Pascal, and that of carbon dioxide is 216.55 Kelvin and 523.9 kilopascal. For binary liquid mixture of alcohol and water in equilibrium with its vapor, C is equal to 2, P is equal to 2, so F becomes 1. Two intensive property may be freely to change. For example, both temperature and pressure may be changed freely over the restricted range in composition of phase, but all three variables cannot be independently changed. If the composition of liquid and pressure are specified, the boiling temperature and equilibrium vapor composition are automatically fixed. A liquid mixture of benzene and toluene containing 39% benzene is in equilibrium with its vapor at 100 kilopascal. This determines the equilibrium temperature as 368 Kelvin and composition of vapor in equilibrium as 61.2% benzene. So this is all about the phase rule. Now let's talk about the Duham's theorem. The state of system is completely determined when both intensive as well as extensive state of system is fixed. The phase rule gives the number of independent intensive variable to be specified to define the intensive state of system uniquely. It does not deal with the extensive state of system. By the extensive state, we mean amount or the mass of the various phase present at total property of system. The Duham's theorem help in establishing the extensive state of the system. It states that for any closed system formed initially from given mass of prescribed chemical species, the equilibrium state is completely determined when any two independent variables are fixed. In addition to phase rule variable, the mass of each phase should be known to define the state of system completely. Therefore, total number of variable becomes P into C minus 1 plus 2 plus P, where the last term is a number of term represent the mass of variation phase. Since the system is closed and from specific amount of chemical species present, a material balance equation can be written from each of the compound C present in system. The total number of equations connecting the variable will more than the corresponding number in phase rule by the C. The number of material balance equation, this is equal to C into P minus 1 plus C. The difference between number of variable and number of equation is therefore 2, indicating only two independent variable need to be fixed to define a state of system completely. This may be either intensive or extensive. If f less than 2, at least one extensive variable must be fixed for the complete determination of system. For example, for water and water vapor in equilibrium, since number of degree of freedom is 1, the intensive state of system is specified by the fixing either pressure or temperature. But the total property can be evaluated only if the amount of liquid or vapor is also specified. However, for the binary mixtures, say water and alcohol, in vapor liquid equilibrium, since number of degree of freedom is 2, no addition specific are need to predict amount of liquid and vapor present in equilibrium provided we know the amount of the component from which the system is formed. Duham's theorem applicable to reacting system as well. But we will discuss Duham's theorem for reacting system in chapter number 3. So this is all about the Duham's theorem. So in this lecture, talk about the vapor liquid equilibrium, phase equilibrium, the nature of chemical equilibrium, phase rule for non-reacting system, and Duham's theorem for non-reacting system. So this is all about today's lecture. I am completing my lecture here. Thank you.